Hi, my name is Joel and I'm a computational engineer at Generative. Today I'm going to show you how you can use the Generative platform to design a quadrupedal robot. To do this, we have linked the parametric geometry, modeled in Onshape, to a gait analysis template. The template sets up a reinforcement learning environment using Majoko to train a walking gait. This enables the simulation of physical metrics such as power consumption and motor torques for different robot configurations. On the experiments page, we can configure the robot parameters, set our objectives and constraints, and start exploring the design space. In this study, I could easily run different experiments, all trying to maximize the estimated robot range, iterating on constraints for the motors, covering both direct drive and pushrod mechanisms. To see the results of the experiments, we move to the designs page. Here we can see the collection of designs for each experiment and explore the data. This view shows an overview of the results from the first experiment. We can easily configure what data we want to see, including visual assets, numbers, and interactive plots. We can also interact with the data through dynamic scatter plots and easily show multiple views to compare metrics. The following plots, for example, show the impact of the upper and lower limb length and ratio on the estimated range, and a plot of the motor torques. With a simple click, we can visualize the constraints from the optimization, see that the optimizers struggle to find good solutions that meet the constraints, with the calf motor torque being the main bottleneck. We can also see that the designs tend toward low-performing solutions with short legs. To study a particular design more in detail, we simply click on it for a deep dive into the metric and can see the particular robot design in motion. With the insights from this first experiment, the hypothesis is that to unlock higher performing designs, we need a bigger calf motor. I can use the keyboard to navigate between pre-configured views to see the plots with data from experiment 2. These confirm the hypothesis to be true. With a motor allowing torques of 100 newton meters, we see a much larger set of designs within the constraints. We can also see that the designs cluster in a more high-performing area of the design space, with limb ratios closer to 1, which we would expect for a robot of this type. For comparison, we're also interested to see if we can get similar performance using a pushrod mechanism, which would allow us to use a smaller motor with 50% lower max torque at the expense of higher motor velocity. This was tested in follow-up experiments, and in the results from experiment 4, in our scatter plot, we can see that the solutions now converge towards a new area in the design space with high performance. It's easy to compare these results to the other experiments as they are visible in the plot as gray dots. We can see that the limb ratio between upper and lower has shifted towards longer proximal limbs, as the optimizer tries to keep the motor velocities within the constraint, but the resulting performance is still on par with the large direct drive motors. Inspecting the constraints on the motor torques and velocities, we see that the bottleneck is now the motor velocity, but we can still find many designs that meet the constraints. From here, we can compare the best designs for each set of motors, compare the outcomes across both input and performance spaces, and make an informed decision about which is the best solution. So this demo shows how we can run multiple experiments and find the impact of key hardware decisions by iteratively refining our searches using insights from the previous experiments.